Wow. All right.
All the folks at home.
Yeah. Okay. To update. Yeah, all the folks at home. We've been going through we've been going through this for about the last hour. We're at proxy type number 1, minimal proxy. Yeah, shoot, sorry about that. Dang, that sucks. Anyway, any other questions?
Is it kind of fair to think of a proxy as like an interface and traditional object-oriented style?
I would say it's fair to think of the logic contract as an interface. Cool. So next, this is proxy type number 2. This is like a transparent proxy pattern, and I'll kind of breeze through some of these so that like if we want to look at code or do stuff like that, we can do that as well. Or if there are any kind of other questions, but I know this stuff is thick, so we can circle around again too. But yeah, so proxy type number 2 that you'll see in the wild is called the transparent proxy pattern. Open Zeppelin. If you look at their different proxy patterns. Kind of this is how this works is like they've just created a basic structure where all transactions fall through to a logic contract unless the sender is an admin. So it kind of handles the deployability stuff. So it just has like a storage slot for the implementation address. So you as the admin could update the implementation address, version 2, version 3, version 4, right? Whatever you'd like. And then specifically this contract here, the yellow contract just manages, it just loads that implementation from storage every time you call it, and then sends it off to the logic contract in order to kind of figure out like what code should execute. But the con here is that you have to manage an admin contract to manage the proxy, and the admin contract kind of handles the deployments and the versioning, kind of things like that. So the TLDR with the code is this, right? So the transparent, so this is the interface. The transparent upgrade proxy kind of has like 4 functions. It has an admin view function. It has a implementation view function. It has a change admin and update to write function. So it has access control, and then you can update the implementation. And this takes an address, and this takes the new admin, right? The key thing here is this if admin modifier. So it kind of has like one level before it interprets the fallback, where it says, hey, if the message.sender is the admin, execute it in, just execute it in this context. So execute admin, execute implementation, execute change admin, execute upgrade to. But if it's not the admin who's calling this function, just execute the fallback function and forward it on to the logic contract to kind of continue the execution flow. And so that's kind of like, that's the TLDR. Show me the code is that like it has these few different ways to kind of manage and roll upgrades, but yeah, that's the transparent. Next is UUPS, which, if I'm honest with you, I kind of ran out of time and didn't have a ton of time to really look into. But it's a way in which you can, where it's like more so that I guess the proxy contract and the implementation contract, the logic contract, are kind of one, and so they call back to one another. So there's no kind of separation of concerns between like admin, where it actually each logic contract, each implementation, all the admin functions exists there, and the code to upgrade to the next contract exists on the implementation contract as well. Upgrades are protected, so it kind of does some callback stuff to like make sure that, like, kind of similar to like safe transfer with ERC, ERC 721. It makes sure that the next implementation contract kind of can handle. It's also it's cheaper to the runtime is cheaper, slightly cheaper gas overwise. The deployment is quite cheaper. You don't have to deploy proxy admin. Calls are cheaper. It's kind of more the industry standard, so I think it's kind of the route you should go if you're looking at creating deployable contracts. And then kind of another proxy type is going to be like the Beacon proxy, whereas like it's kind of the same like factory pattern, so this kind of parent-child pattern, but actually all the children point to a beacon, and that beacon can be upgraded, so you can actually roll in and out, right? So like you could have there could be n amount of time between like these proxies being deployed to say that these are Gnosis safes, right? This is my smart contract wallet. So I deploy it on its own address, right? And then this is its own address, and this is its own address. But every time a function in here runs, it's going to go to the beacon, and that beacon handles its own versioning. So it's a way that you can have kind of multiple child contracts, kind of still from this like factory pattern, but the actual logic implementation can be upgraded for all of them. So it's like a separation of concerns between proxies, but the way that those proxies behave are determined by like a central authority, right? So like you could say kind of that like your iPhone is kind of like a beacon pattern that Apple's going to force. You buy your iPhone, but you're going to stay up to date even though your iPhone belongs in your hand, right? It's like it's your device, and you can kind of have a similar pattern with these smart contracts here.
So that's just saying like instead of 100 contracts that you have to update 100 addresses, they just all point to this beacon.
Correct.
Just the beacon, so that those are always static, but the beacon is going to have another fallback that is redirected.
Yeah, exactly. So it's a fallback to a fallback because that beacon is upgradable as well, or at least I think that. I don't know. I haven't peeled back the implementation yet, but I could assume. Yeah.
The pattern is a proxy on top of a proxy.
Yeah, exactly. Like kind of like once you start with like number one here, like the minimal proxy, it's kind of like the whole like dimensionality thing where it's like a new dimension folds out. You go 2D, then you go 3D, then you go 4, right? Then you get depth, and then you move through time, and there you go.
I got a question on the universally upgradable proxy.
Yeah.
When you say upgrades are protected, what does that actually mean?
So when I say upgrades are protected, that means that there's actually a callback. So like with this transparent proxy pattern, when you say new implementation, the contract, it's not a standard of the contract to actually do some introspection upon new implementation to ensure that new implementation conforms to a spec that is flexible and like as it should be. Whereas like UUPS actually performs some like runtime introspection, specifically around storage slots, because there's been some interesting EIPs to standardize how storage slots are, I guess like read and written to when it comes to proxies. And we can actually go into that because it's interesting if people want to hear more about that. But it's like they chose a specific slot to always read and write from, and so that they can avoid storage slot conflicts with like 0, 1, 2, 3, 4. Kind of that's.
So what happens if you're violating whatever the interface of that contract should be by providing an address to something that's not compliant, then it rejects the upgrade?
Correct. Yeah, it will reject the upgrade for you because like if you make a mistake within that transaction, you've essentially bricked you bricked the contract forever. So they really have tried to create a standard to hold your hand, kind of through that process because it's smart contracts were never meant to be upgradable, right? They're supposed to be immutable, which is why it's kind of so hard to do patterns like this. But
so what do they enforce? Like, is it a certain set of EIPs that they enforce for certain contracts?
Yeah, correct. So and what it does is it enforces. I can show you exactly on here actually. It enforces EIP 1967, which is proxy storage slots, which defines a function called Bum, 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 bum. Now this is all admin slot, get beacon, set beacon, upgrade beacon and call, proxy, delegate. I think that there's a function in here called UUID? At least there is in the code. If we look at ERC 1967 upgrade, here is the upgrade function, upgrade UUPS, and so what it will do is it will wrap the new implementation in this interface, and it will try to call the proxyable UUID function on this contract here and assert that it equals a constant. So the this is defined where proxyable draft ERC. It's somewhere here. Come on.
That's okay, I can research that.
Yeah, it's oh yeah. So here it is. So it's a view function. It's a UUID, and it's the implementation slot is the hash of like a string actually that they kind of create that they condense into like a bytes 32 value. So that's what it's actually doing is when you call upgrade, it's enforcing that contract. I mean, unless it's been written maliciously, is going to store values the same that the current implementation attempts to store values. Any other thoughts?
I had a question about the UUPS. There's nothing that indicates to the callers of the function that the underlying proxy contract has been upgraded, right?
Oh,
You
like
could be interacting with contract A, interact, and then day 2, they could have changed it.
Correct.
And you don't necessarily know.
You don't know anything.
Yeah.
Exactly. Yeah. So you any DApp, any vault that has a upgradable proxy pattern could write an upgrade to themselves to withdraw your tokens tomorrow.
So, yeah, and the reason I asked that is I recently just learned, I didn't know this, but like USDC is a proxy contract with UUPS. That I was floored.
Yes, correct. So actually, we did that kind of in like our episode 0 of Solidity deep dives, but we did a USDC ether scan, and what gave me a little bit more of a I don't know, not necessarily a warm feeling in my heart, but just made me feel a little bit better about it.
It's verifying the proxy now, right?
Yes, exactly. Yeah, so you can kind of read his proxy and write his proxy. If you look at the, I believe if you look at the, where is the?
We had a version read function at the bottom.
There was a version function.
Yeah.
Symbol version. So this is version. We're on version 2 of USDC. There's a pauser. There is an owner. There is a.
Wouldn't the owner be in the regular read contract, not the read as proxy?
The storage is actually all set, but yeah. So here's the implementation. I don't know why that isn't reading actually, and then the admin. That's kind of strange. Yeah, no, that's exactly that's where the blacklist is. Oh yeah, okay. So this is a proxy contract. Oh, I think the reason is because we're not calling this as the admin. It's kind of strange, but I'm pretty sure that this upgradable proxy has been. I think the proxy admin is 0 at this point, so I don't think it's upgradable anymore. I could be wrong. It might have to be like
There's
let's see, Google, let's see, storage, proxy read, admin. I don't, the issue is we're actually, it mentions this in the Open Zeppelin, we're getting delegated out. So like, remember that if admin modifier that I was showing you? I'm not calling as the admin, even though I'm calling a view function. So
Was it falling back then?
so it's actually falling back to the implementation contract, which is why it's not returning me an admin. So we could, right, so yeah, there's this change admin, there's a upgrade and call, there's a upgrade to, but if I read admin, there's actually no return. And I believe that's because, so if you look at the proxy docs, if you look at the transparent upgradable proxy, if you call admin, here's the tip. To get this value, clients can read directly from the storage slot shown below, specified by the eth get storage at RPC call. So unless someone has a RPC like a debugger that I can use, or like cast could do it. Yeah, okay, all right. Just to, so if I go cast storage, I'll try to get the cast storage at the address, at the USDC address, and at the storage slot this, and the RPC URL should be, shoot, let me grab a RPC URL. I don't know if this is interesting to anyone or if this is like a true rabbit trail, but mainnet, eth mainnet, and then the mainnet infura.free, and then the infura API key is this. Yep. First try. Dash RPC URL this. Okay, yeah, so I think, right? I don't think it's upgradable anymore. Could be totally wrong about that. I could be being a noob. I might have no idea what I'm doing, but
So at least there's at least not an admin set currently.
I am
Probably.
probably you.
Theoretically, if you relinquish ownership, then who's the owner to set a new admin?
Right.
Right. Yeah. So, sorry, that was a bit of a rabbit hole on my part, but yeah, this is a proxy contract, but you can also renounce ownership. I believe you can do that with UUPS too. Is you can actually not implement the upgrade to function and signal to your users that, you know, you've been through a couple implementations, you've had this logic contract for a year, you believe it's safe, so you're now going to relinquish your ability to update this code. And I think that that's reasonable, because I don't know, I go back and forth on it. I don't believe in like forever upgradable contracts depending on the use case, but I do think it's a nice. I think it's a flaw to believe that you can write bugless software. I think it's like a lot of hubris. So I go back and forth. Really, it's the weird part about blockchain, right? Is there's no undo button. Any other thoughts about UUPS? And
I'll share one more thought. Maybe 5-6 months ago, we were developing something, and we felt almost forced into proxies for, I think, part of the reason that you're describing, but maybe it was more about trashing the state of our storage. And every time we wanted to make a significant enough change to the product or to the contract, you were always faced with this dilemma of like, Okay, well, unless we have a proxy or an upgradable contract,
Right.
if we upgrade this code, like, we're just gonna nuke the current state and whatever was happening in the product at that time. That was always a really crappy decision to have to make.
Yeah.
So that really pushed us into, well, now, I mean, we really should be developing these as
Mm.
proxy contracts, storage over here, and then we can continue upgrading our logic over there.
Right. Yes. Yeah. No, that makes sense. You want like I think there's a ton of nuance in writing like resilient upgradable contracts that aren't brittle when it comes to like upgradability because if you flip storage variables, then every reference where you say balance of is now going to reference name, and it's going to return a string and revert and break, right? Because it wasn't expecting a name, and now it has to interpret arbitrary bytes and like so stuff like that is like there's so many gotchas when it comes to proxies, and they're kind of a beast. That's why you see like some interesting patterns.
Do you know of other projects that are using these patterns? Or more popular ones?
Yeah, all the I mean, I guess the first one, like, most ERC20 tokens I feel like are that I see are kind of like follow this proxy pattern, unless they're like a really decentralized first kind of team. A lot of people are writing proxy contracts, like for example, like all of Badger vaults, that DeFi project. Those are all proxy contracts, and they're pausable, right? And they're upgradable, and they're you look at it as like V3, and you look at their code base, and it's like they're like double underscoring variables and saying unused just to like maintain the storage gaps. It's like it's no fun. But yeah, there's a lot of stuff in the wild. Anytime you see, because all this stuff exists in the bytecode, right? So Etherscan can read it. So anytime on Etherscan you see these kind of like read as proxy or write as proxy, that means that like what it did is it asked the base contract that you're on here. It asked for what the it found the implementation contract in the bytecode, and that's from a standard as well, right? There's an implementation call. So you just do like an implementation read against the contract, and then you go to that contract. So it's not serving us the contract ending in EB48. It's giving us the ABI for the contract at BDCF, and then this would be previously recorded to be on here. So this was V1, right?
So this is not the parent proxy, but the child logic.
It's the implementation, yeah, the implementation contract, the logic contract, kind of whatever you want to call it, right? The proxy is the gatekeeper. The proxy has the storage. The proxy has the ether balances, right? And then now when we do read as proxy, we're actually, I think this wording is kind of off, but if we do read as proxy, now we can kind of see what the implementation contract, the logic contract, actually does here. So there's like, I guess there's a rescuer address. That's interesting. There's a master minter, which we all knew, which is a contract here. It's like the USDC master minter, and they get to decide how much to mint or not to mint and when. You can go see all the transactions that have happened, where there's been a lot minted or not. A few final notes that I just wanted to say. Yeah, I have these definitions here. So like anytime you see master copy, anytime you see singleton, implementation, beacon, that's going to be where the logic resides. You can't use constructors in upgradable proxy code. So you have to write initializers. OpenZeppelin has like a great spec for this. But constructors, and this kind of has to deal with how the EVM with how Solidity will bundle and ship code for you, is you get two flavor. You get runtime code and you get deploy code. So runtime code sets up immutable, like constant variables to be kind of injected in the bytecode, and then it will execute the constructor and then also return the runtime code in a single transaction. And so that's what the deploy time code does. And then and then you have the runtime code. But when you're trying to bypass all that stuff, when you're doing shady stuff with initializers and proxies, you don't get any of that deployment code. You only get runtime code. So you can't write constructors. And then if you're writing this stuff, always, always, always use the OpenZeppelin hard hat plugin when developing with proxies. They protect you from a lot of gotchas. They really try to make this stuff safe for developers. Don't be a hero, right? Just like, use the plugin. It'll help you figure out and match storage slots. It will actually reject your upgrade path if your upgrade path is incompatible. It does a whole bunch of stuff to detect in flight if your upgrades are compatible, if they're going to break your stuff, or if they're going to work. Yeah, so those are that's kind of all I had for the slides. I kind of ran out of time, but we still have time until like 8:30 for questions, or if people wanted to dive into code. Yeah, just open floor on proxies and questions and code.
I have a kind of random delegate call question.
Yeah.
So does it ever, can it ever change the state of the contract that's like getting the logic from, or it's always only gonna make where the context was executed?
It's always going to modify storage in the context where it's executed.
Okay.
Yeah, so unfortunately you can't reverse delegate call.
We should.
Because I really wanted to do that to like modify message sender, right, or a message value. It seems super useful, but then you think about it more and you're like, oh, it's actually super unsafe, right?
Like
because like imagine if I could delegate call USDC and change its balance without me having to go through one of the protected USDC functions to modify my balance, right? You can never. It's really just for delegating logic. The storage still exists at that place.
Is it only used for primitive types to share, or to be able to share between the delegated call?
So actually, so there's, I'll show you what the proxy, and let me know if this doesn't answer your question and stop me early on. But like if we go to OpenZeppelin contracts and open up proxy, this is the delegate function, and we can walk through the assembly here. So call data copy takes the memory offset, the data offset, and then the data length. So what it will do is it will copy the message data. So if you remember at the beginning of the presentation, it will copy all of this stuff into memory, and then pass. And so now the memory now all that exists at memory address 0, and then it will pass when it does the delegate call. You see this third variable here in offset. That's going to be like where the memory that's getting passed to the delegator function starts. So then we pass it that memory reference of 0. So basically it just loads the call data, all the call data that was passed to it within this transaction. It loads all, like, don't pay attention to this. It just loads all the call data from this transaction using this this call data copy opcode or assembly call. So it copies all the call data and then just forwards that call data along.
So that means if you have structured data like struct, they better match, right? Whatever you're using, whatever the logic's using, they better match, otherwise you're going to be messing up the call.
In storage, yes. In storage, the slots have to align.
Right. I mean, in memory, most likely it will fail.
So we'll actually, this delegate function doesn't have to know anything about memory. A memory is like a volatile array. So it's just like, it's, it's like just an array with like n amount of items inside of it, as you could see from that goofy transaction that I passed that was like hello world, like, hey world. It literally doesn't even have like an even length call data. It's not padded to 32 bytes or any of the things that you normally see. So it's just like a memory array, right? And so it just forwards that entire memory array for the logic contract to figure out what to do with. And then this next call, it returns it will load, it will copy the return data to the 0 slot in memory. And then revert with that call data or return with that call data, depending on if it fails.
So you're just copying the call data, calling with the copied call data, and then getting a return value, and then copying the return value, returning the copied return value.
Totally.
Yeah.
Exactly that. It just like is like, hey, I got something, deal with it. Okay, you dealt with it. What did you say? I don't care. Here it is.
Yeah.
Right. So it just because with the EVM, the return data and calls like that, they don't bubble up by default. So you have to handle the bubbling of each return of each like teardown from the previous state. So like for example, like this creates its own call, its own execution context. This return data copy just loads whatever the result is from that execution context, and then either returns or reverts it.
Yeah, doesn't it just build a stack, basically? And that gets torn down, and then it has to build a new one for.
Yeah.
Yeah.
Yes. Yep.
That's a good question. Does that allow you to get around stack limitations?
Yes. Yeah, it does. Because the stack is going to be cleared on each external call, and you're going to start over again with a fresh stack and fresh memory. So you get 0 memory, 0 stack, and then but you have kind of this ephemeral call data there that you can use or not use. You can accept, you can use it, you can reject it, right? Like EVM is such a simple stack machine. We don't realize that so much of the stuff is done by Solidity, not by the EVM, right? Like memory management, things like that. It's like, hey, contract starts doing something, and then Solidity kind of handles how that works and how it ingests call data and returns call data, uses revert opcodes, things like that.
What about gas estimates? Like, does it carry through?
So that's going to be handled by the client. So when you run when you do a call in MetaMask, what it will do is it will execute it will do its own gas estimate to figure out how much gas it needs to execute that transaction at that point in time. And then I'm sure it sends a little extra gas stipend just in case storage has changed or whatever happens intra-transaction. Not intra-transaction, but like before your transaction gets processed, to be specific. And so when you, oh yeah, it's perfect, it's right here, right? So yeah, like I cryptographically sign how much gas I'm willing to spend as part of the transaction that I send. Also the gas price I'm comfortable paying. So like, for example, I say the gas limit is 100,000. Then this gas call here, it's what's left, 100,000. Exactly. So it'll forward along all the gas that I passed onto it, right? So like I could say whatever I wanted here. I could say like I could do 100,000 as like a fixed constant. I could most likely do like 20,000. You see this pretty common for like read calls where they want to ensure that the calling contract doesn't do anything nefarious. You give it a gas stipend, but in this case, you just want to kind of forward everything along to the logic contract because you trust that the client has computed how much gas they're going to need off chain, and then they sign and pass that to the blockchain to handle and spend for you. And then here's this little like hover here. You see like the gas, the address that it's going to, where the call data, where the next call data will begin, and then how long it'll go, how long that call data goes for, so the call data size, right, that could be, you know, an amount, but it's sort of starting at, you know, 0 and going to however long. And then return offset and return size is you could actually say like where you want that allocated. So, but the reason why that's 0, 0 here, we're not actually storing the call data back in memory yet, because we don't actually know what's going to be returned to us. So we need to actually ask the blockchain, what is the return data size from the last call, from the last state. And so that's why you kind of do this call, which is return data copy, which copies the data from the return data buffer, and you have to kind of figure out how that's most likely going to be variable length. So you copy it to the 0 memory slot, you know, starting at 0 to however long it was. And so really this delegate, like this is it. It's super low level, super bare bones. And then kind of the fallback function just delegates all the calls to the implementation. And this is the base abstract contract for proxy in Open Zeppelin. And they have like a few different things. So you'll see in here some of the ones that we talked about. Clones as minimal proxy. You see UUPS upgradable. You see the transparent proxy. You see ERC 1967 proxy is like the slot, and I believe it is also UUPS, kind of bundled into one. And then Beacon Proxy just kind of, yeah, it's I don't know if Beacon Proxy has a standard, but yeah, that's the Beacon Proxy that we discussed.
Is there a competitor to Open Zeppelin? Are they standard now?
Okay, yeah, there is, I don't know if any of them are watching, but wait, there's GeoWeb Project, if you know Graven. He's a crypto rado OG, but his project, GeoWeb, I'm helping work on their project with them. They actually use, there's another standard that I didn't even get to in this talk called the Diamond Standard, which is a standard for storage and for proxies that kind of allows for, it's just like a little bit more flexible on the storage side of things. So you can have like certain function selectors go to certain implementations and other function selectors go to other implementations. And so it's like a mapping of function selectors to implementations. And so they're using beacons and diamonds and beacon diamonds, and they're doing some crazy stuff, but they're, let me find it. It's, wait, it's in there, it should be in their package JSON. It's called Solid State. I don't know much about them, but yeah, solid state contracts. Yeah, so these are, solid state network. Yeah, Brave search is not very smart. Solid state network is a upgradable for Solidity smart contract development library. So they kind of have their own spec as well that helps with diamond storage, and it's kind of built for upgradability and follows these different patterns here as well. There's also Soulmate, which I like. It's written by Transmissions 11, who works at Paradigm, and they also worked on this with Rari Capital. And there's some other really smart folks like Vectorized, also known as Optimizor, the guy who made ERC 721A, and Ross Campbell from SushiSwap, and a whole bunch of other like kind of big brains who kind of contribute to this. This is a little more like open sourcey, less corporate, super gas efficient. They're not terribly flexible, but they have a lot of the really minimal deployment size and very gas optimized contracts that have all been audited. And so they've got some good utils here, like for casting, for math, for fixed point math, for Merkle proof stuff. They've got base tokens, so ERC 721, ERC 20s and 1155s. They also have some standards for like 4626, which is a vault standard, and then there's like an auth standard too, which is like one that has roles, and then one that's just like simple, like ownable, like Open Zeppelin. Open Zeppelin's ownable. I haven't found any other ones actually so far, but yeah, this is like the degen version of Open Zeppelin. Yeah, anything else? And I guess we could kind of wrap up early too if all the questions are done. Or
Do you see any like creative abuses with the storage slots? Seems like something that would be taken advantage of.
I mean, it can definitely brick your contracts. I think like since there are a lot of admin privileges around upgrading implementations, I think it's kind of hard for you to leverage yourself. You are gonna have to worry about like more just like pitfalls. Like you are gonna have to worry about dirty storage. So like for example, if you want to make your storage values something else and you're hard overwriting those things, say that like you in the past had UINT 256s or 32 byte values in a mapping, and now you want to store addresses in the mapping. Well, the upper 12-bit bytes of those values are all going to be dirty from the last 32 byte reads. Stores. So like there are like a whole bunch of nuances that you have to think about when it comes to that. I think there is an issue with uninitialized proxies, which has been kind of a big attack vector that's happened to a few different projects. But if you have a proxy, actually, if you have if you have a implementation contract, so like a singleton or a master copy that has some type of base code in it that can be modified, then you essentially, by calling that singleton directly, you could modify all subsequent clones or proxies of that. You modify the functionality of those proxies. And so you have to make sure that Open Zeppelin does a pretty good job of this stuff, because if you look at how they handle proxies, they have these different modifiers on here called here's clones, right? And clones is a way for you to make if you had a contract that's clonable. I'm trying to find I think I have it open in VS Code. Initializable. Yeah, it inherits off of initializable. And so if you have a contract that's initializable, like you want a modifier to say that hey, this contract is only initializable once, because someone could come along and try to reinitialize your implementation contract, your singleton. And if they can reinitialize your singleton, they might be able to change something fundamental about the byte code that's then subsequently copied or looked up to, delegated to. So cool. Yeah, that's like a primer on all the different types of proxies out there and some of the pitfalls. You can go really deep into proxies, and you should go way deeper into this into proxies if you're going to ever deploy something that is in production. So this was just like a little bit to kind of whet your appetite about it. Some of the pitfalls, some of the common patterns that you'll see, and then some of the fundamental aspects that make it up. But yeah, thanks so much, guys. Thanks for coming.
Thank you.
But yeah, I'll put my Discord handle in my Telegram. I love working with people and answering questions. So like, and I'm super active around here in Denver. I live 10 minutes up the road, and we're gonna have another one of these next month. Try to squeeze one in before.
December 12th is our like 80% date. We just have to make sure we can lock in the space.
Correct.
And Colin has to check his calendar.
Thank you.
Assuming those things work out, December 12th, Monday. No, Tuesday?
Yeah,
13th, I'm
Tuesday.
sorry. December 13th.
The 12th is X-Denver.
12th is X-Denver. 12th X-Denver, we're doing a what the fuck is DeFi, so geared more towards beginners. We had a lot of people come out who weren't exactly beginners, so you're certainly welcome if you're not a beginner, but just know it's going to be more